Alright, in this video I'm gonna show you how to model a truss in ANSYS. Alright, so let's look at the problem statement. We're looking at a 3-bar truss, this one. So as you see, let's see if you can make it larger. Alright, so it has 3 elements, 3 bars. Let's see, point 1, we have a roller support that is free to move in vertical direction. At point 2, there is external force of 100 kilonewton and it's free to move in X direction. And at point C, we have a pivot or pin support, so it's not gonna move, but it's free to rotate there. So external force that we have is 100 kilonewton force, as I said, acting at point 2. Modulus of elasticity is 100 gigapascal, and cross-section area of our bars are 10 to negative 4 meters squared or 100 millimeters squared. The length of members are all 1 meter, so the angles between the members is 60 degrees. So we would like to find node displacements and also reaction forces using ANSYS. At the end, when we are done with ANSYS, we are going to come back here and do the problem by hand, do the FEA by hand. I'm going to show you the process, how to model this by hand. Alright, so let's go to ANSYS and mechanical APDL. So our model is going to be structural. Then we have to use element type link element. I'm going to activate that. Then in the previous models of previous versions of ANSYS, cross-section area had to be input using real constants, but now we have to define it under sections. So we go to link element and you see sections, and for link you go pick 1 as your element ID or section name, and the area I want to use millimeter squared, millimeter as my unit, so 100 millimeter squared is my area, so we define it. Then we need to define material property, so it's structural, linear, elastic, isotropic. I'm gonna use millimeter and a megapascal for my stress and elasticity. Modulus of elasticity is 100 gigapascal. In megapascal, it's gonna be 100,000. So let me put here 100, 1, 2, 3. We don't need Poisson ratio, but you know, you can put 0, or for engineering metals is usually around 0.3. This is not going to be used in this model, so it's not, doesn't really matter. But okay, so I don't want to leave it blank, so I just say okay and close this. Now we go to modeling. We have to define the key points first. So key point 1, I'm gonna put it on the origin, so let's see, 0, 0, 0. Apply. Point 2 is at node 2 is 1 meter to the right, or 1000 millimeter to the right. That's point 2. And point 3, x coordinate of that is 500 millimeter, and its y coordinate, let's see, if you look at the model, like it's 1 meter. This angle is going to be 60 degrees, so it's gonna be, let's calculate that, So it's 1000 times sine of 60. So 60 degrees sine times 1000. It's gonna be 866, right? Yeah, sine 866. See if I can copy this number. If I can copy it, paste it here. I'm not sure if we can do that, but let's try it. Yeah, it's possible. Okay, so 866. Okay, so I have my 3 points, key points. All right, then I'm gonna create lines by connecting those key points. This to that, 1 to 2, 2 to 3, and 1 to 3. And these are my lines. All right, next step is gonna be meshing, but we need to define mesh attribute. I can pick all the lines, and for all lines we have material number 1, element section 1, then the element type is link 180. So okay, so next thing is mesh size. All lines, every line I'm gonna just put 1 element on them. That's sufficient. Alright, so what else? Next is the meshing itself. All the lines, we're gonna mesh them. Now we can go to list, see the list of our elements and their attributes. Now 3 elements total, material model 1, element type 1. So section number 1, the nodes that the end nodes for each line element, you see them here. Alright, so it looks like it's been done right. Go here, analysis type, static, define loads. Alright, so we go here, apply, structural, displacement, and key points. Okay, first this key point, the number 3, is gonna be fixed in all directions. This key point, this one, is gonna be free in Y. So I'm just gonna fix X and Z. And for this guy here on the right, what we have free, X is free, Y and Z are fixed. And then also we have a force on this key point. So our force was 100 kilonewtons or 100,000. Alright, let me double check we had that one right. Yes, 100,000. Okay, so we are ready to run it. Everything is set. So running the model, current load. There you go, solution is done. Now let's go look at the solution. So always look at the deformation first, deform shape. On deform, see if the deformation makes sense. It looks like it makes sense to me. You can see animation also. If you want to go see animation, you can go to result viewer, change here to displace the structure, and I think if you do this, animate, okay, animate the deform shape. You can here determine how many frames you want to make. By doing that, the more frames you have, the smoother the animation is gonna be. So here you can change the speed. see it shows deform versus undeformed. So this is how you can see animation here. So I'm gonna go back to the model and then see some numbers. To see numbers, we go to list results and let's see reactions. So at point node 1, we have reaction negative 80,000, and node 2, which was this one, we have vertical reaction of 34 kilonewton or 34,000. Node 1 we had negative 80 kilonewton. And then on node 3, here we have two reactions. 20 kilonewton going to the left, and then 34 kilonewton going up. Alright, so let's see nodal displacements. You can see everything here. So we have 8 millimeter at node 2. We have 8 millimeter going to the right. All other ones are 0. Alright, so here is the solution from ANSYS. Now let's go to hand calculation. It may be interesting to some of you guys. So for truss elements, the element stiffness is gonna be like this, using this equation. So element stiffness is gonna be AE divided by L. What is A? Cross-section area. E is modulus of velocity. Length is the length. L is the length of the element. And then theta is the positive angle, the angle that element makes with positive x-axis. So here is that. And so here we had 3 elements. A, E, and L is the same for them. But element 1, which was connecting 1 to 2, the element stiffness is going to be like that. Theta, put theta equal to 0 in that equation. I took AE L out. I'm going to input the numbers there at the end. Element 2 makes angle of 60 degrees with x-axis, so you put 60 degrees, and here is going to be like our stiffness element, our element is stiffness. And then for 120 degrees, the last element, you're going to have this. And if you assemble all stiffness matrices, the global stiffness matrix is going to be this. Again, AE divided by L is out. Alright, so here's a number, and then you go down. So in global coordinate, the equilibrium equation is going to be this: force equals global stiffness times the displacement, node displacement. Node 1, we know that it's not going to move in x direction, so u1 is going to be 0. We just have vertical displacement there. Node 2, this was opposite. It was free to move in x direction, but in y direction it was fixed, so v2 is 0. And then for the third element, it's completely fixed. So u, horizontal displacement, and vertical displacement both 0. And force wise, if you go up, look at the model. We have external force only at node 2, which is an x horizontal force equal to 100 kilonewton. Node 1 and node 3, you have reactions. And node 1, we have horizontal reaction. Node 2, by the way, you have a vertical reaction. Node 3, you have 2 reactions. So total is 1, 2, 3, 4 reactions we need to figure out. Alright, looking at the equations, you see u1, v2, u3, v3, we have all of those. And f1y, we know it's 0 because it's free to move. There is nothing there. And F2x we know is external was 100 kilonewton. Using the third row, which is my equation, like a third equation, you guys can find, since I have F2x, I can find U2, which is nodal displacement of node 2. If you do that, you know, that equation, U2 is going to come out 8 millimeters, which is matching what we had in ANSYS. And once you have that, once we have used the third equation and found U2, which is my only unknown displacement, then the right side, everything we know, and we put multiply K by that vector, and then we're gonna find the reaction forces that we are looking for, and they're gonna come out exact same as what you had in the ANSYS. F1x negative 80 kilonewton, F2y negative 34.6 kilonewton, F3x negative 20, F3y 34.6 kilonewton. They're matching the ANSYS. So I hope you guys find this video useful.